In this video, we discuss infinite series and its convergence or divergence. First of all, let's discuss some terminologies. An infinite series is a sum of infinite numbers. If we write it out, the sum the summation represents the sum of infinite numbers. Now, if the sum is a finite number, we said the series converges. If the sum is infinity or cannot be determined, we said the series diverges, or the series is divergent. One thing we need to talk about is since we care about whether we can find this sum as a finite number, so it's important to focus on the terms in the sum when the subscripts are large. What I mean is, this basically is the sum of infinite many terms. So whether the sum can add to a finite number depends on its tail. Let me write it here so you see better. And so on. So by tail, I mean if we truncate the series anywhere, there could be, from this, before this point, there could be thousands of terms. As long as it's a finite number of terms, they always add to finite number. So the tail, that will actually determine whether the whole thing can add to a finite number. For this reason, a lot of time when I write the infinite series, I basically just write it as a bang, unless I care about exact value. So I just write sigma an. N can start from any number, doesn't matter, because for convergence divergence we care about the tail. Now let's get some basic idea how we're going to try to check whether series converges or diverges. Let's say we try to plot those numbers in the sum. Say A1 here, A2 here, whatever value. So this way we get a bunch of them, just A1, A2, A3, A4, so on. Now we want to see whether the sum of those numbers is a finite number. Well, check out this scenario. If all these numbers will come down eventually, let's see a different graph. This is the case in calculus, described as a sequence approaching 0, getting smaller, approaching 0. Now what if this is not true? If the limit is not 0, mathematically, the limit of sequence is not 0 means no matter how close you draw a line to y equal to 0, the x-axis, you can always find infinitely many members among the sequence that are greater than this whatever value we call the epsilon. So what it means is given any small number, there are always infinitely many guys that form a subset of A sub n that are greater than that. Remember, infinitely many of them. If that's not true, well, we would claim in math the limit approaches infinity. Alright, so no matter how small number we pick up, again, this is our assumption, the opposite of limit of A sub n equal to 0, A sub n approaching 0. So for such small number, let's describe this as using mathematical notation. A sub I1, A sub I2, A sub I3, infinity of them. So those guys are part of the whole thing. Now, if we check sigma an, well, sigma n would be those guys, add up infinity of them plus the rest of them. Now we assumed there are infinitely many of them that are all greater than epsilon. Therefore, the sum of this subset alone is infinity, because everyone is greater than epsilon. So it's like a the infinity is like infinity times a small number, which is infinity. Therefore, this is series will diverge. This series will add to infinity. This part is infinity alone. So the whole series will diverge. This will happen mathematically when the limit is not 0. Because of this study we come up with our basic test for divergence, called the nth term test for divergence. It's exactly what we just discussed. It says if the limit of the sequence as n goes to infinity is not 0 or undefined, then the infinite series will diverge. Again, doesn't matter, n start from 1 or 0 or whatever number. This test says limit being 0 is a necessary condition for series to converge. If this necessary condition is not satisfied, it will definitely diverge. Now let's see some example. So we have an infinite series. Here A sub n the general term is n squared minus 1 over 3n squared plus 1. Well, let's check the limit. N goes to infinity, limit of the general term. What's the limit? Let's see. When n goes to infinity, n squared goes to infinity. Infinity minus 1 is still infinity, the bottom 2. So it's infinity over infinity. We could apply L'Hopital's rule to differentiate top and the bottom, and then again. So L'Hopital's rule twice, so we can find the limit. Or we can simply drop the 1. So that's a lower order term compared to n squared. The 1 from the bottom also dropped. It's very easy to find the limit. 1/3. If you apply L'Hopital's rule twice, you get 1/3 too. So the limit as n goes to infinity of the general term a sub n is 1/3, not 0. Limit is not 0. Therefore, we say this series diverges, or this series is divergent. If we use the graph to make sense of the result, what it says is those guys, when n is small, we don't quite care. They can be whatever value, a1, a2, a3, a4, whatever. Since the limit is 1/3, we can guess when n is large enough, all those guys are pretty much like 1/3. That's what the limit means. In other words, you can totally forget about the first finite number terms, first 5,000 terms, first 6 million terms. Doesn't matter. We care about the tail, the terms when the subscript is large. So those guys are all more or less like 1/3. Therefore, there are infinite many of them back here, the tail. Now it's like adding infinity many 1/3 up. Well, of course, the answer will be 1/3 times infinity, infinity many of 1/3. No wonder the series diverges. Alright, let's see another series, another example. Okay, we identify the general term, which is inverse tangent of n. Now, what's the limit as n goes to infinity of the general term, inverse tangent? Well, let's try it out. When n goes to infinity, so this is approaching infinity. What's the inverse tangent of infinity? What's this? If you're familiar with trig, inverse trig, the answer is pi over 2. Because tangent pi over 2 equal to infinity. The graph of tangent pi over 2, value of tangent is infinity. So from trig, we figure out the limit of the general term a sub n as n goes to infinity, pi over 2, not 0. Not 0, so the series diverges. And again, if you try to picture values involved in this sum when n is large, since we know the limit is pi over 2, therefore we know when n is large, all those terms involved in the sum are pretty much like a pi over 2. Pretty much like a pi over 2, so it's like adding infinite many pi over 2 up. Of course, that's infinity. The series diverges. So this test is very simple. It's very easy to use. Just check the limit of the general term s of n. It's not 0 or undefined. You say the series diverges. What we need to care about is, given a series, you check the limit. If the limit is 0, the test doesn't say anything about convergence or divergence of the series. It only says when the limit is not 0, series diverges. Now let's check out two series in this example. The first one, a sub n is 1 over n. It's easy to see it approaches 0. What can we say about the series in terms of convergence, divergence? Nothing. The test only says when the limit is not 0, we can draw a conclusion. Series diverges. If the limit is 0, we don't know. As a matter of fact, this series diverges. If you write out, it's 1 over 2, 1 over 3, 1 over 4, 1 over 5. How do I know this thing diverges? It's not because of the test. Because the test says the limit not 0, we can say it diverges. We can do some simple math to figure out. Let's create a new series based on those guys. Let's see. Say, copy down the first two terms. It replace 1/3 by 1/2. Well, actually, not replace 1/3 by 1/4. And then replace 1/5 by 1/8. So those two terms all become 1/4, and then the next 4 terms all become 1/8, and so on. The new series is essentially, there are 4 of them here: 1/5, 1/6, 1/7, 1/8. 4 of them is 1/2. So the new series is essentially the sum of infinite many 1/2s, because there are infinite many more grooves coming up. Of course, that's infinity. It's like infinity times 1/2 plus 1. That's infinity. So we know this guy diverges. From the way we come up with this series, we know the sum here is greater than the sum here, because we got a smaller values. 1/3 becomes 1/4, 1/5 becomes 1/8, 1/6 becomes 1/8. So a lot of those values in the sum are smaller than the corresponding values in the original sum. So if this is infinity, that's infinity. So this thing diverges. Well, this series just shows when the limit approaches 0, the series could diverge. Now, next one. Say n from 1 to infinity. This one you write it out. It's 1 over 2 square, 1 over 3 square, 1 over 4 square. If you check the nth term, approaches 0 when n goes to infinity. Yeah, we can show later on this thing actually converges. So this in this example, just want you to see that when the limit of the general term n goes to infinity is 0, the series could diverge, the series could converge. This test basically fails. We cannot determine one way or the other. We have to do something else. So again, when you check the limit of the nth term, only when the limit is not 0 can you draw a conclusion. Can you say the series diverges? If the limit is 0, the series could diverge, series could converge. Now, how do we do it? This, of course, was simple. We can actually do some simple math to figure out, and this will show later on how to show the series actually converges. Now let's define sum of a series. So we can check out, in addition to the test for divergence. Well, this considers a definition too. The sum of infinite series is defined as limit as n goes to infinity of s of n. Well, s of n is the sum of the first n terms in the series. Now, notice I use I as the subscript here. It doesn't matter what letter we use as a subscript. We can denote this as a sigma an, n from 1 to infinity, or ai, I from 1 to infinity. If you write out each, it's the same sum, same series. Reason I use I here is I want to use the n for subscript of s of n. We call nth partial sum. Now let me write out the s of n so you can see better. So s of n is a1, a2, a3 up to an. Imagine when you increase the subscript, you would have more and more terms in the sum. As n goes to infinity, well, you would have all the infinitely many guys from the original series. So you can kind of visually see in the definition. The left side, original series at a1, a2, a3, all the way no end. This of course would be like when you send n to infinity on this side, just have more and more keep going. So the definition here really just represents this. Well, from the definition we can see, in order to determine the sum of series, we check the limit of the sequence. If the limit of the sequence is a finite number, the series converges. If the limit is infinity, diverges. If the limit is undefined, we also say the series diverges. The definition also provides us a way to check convergence, divergence of some series. Let's see this example. This is considered as a telescoping series, years in Y. Now, I want to go by the the formula in the definition. So let me just turn this to this way. I can use n for nth partial sum. This is the same thing. So my nth partial sum is, well, the sum of the first n terms. We factor, the denominator will have a 2i minus 1, 2i plus 1. If you write it out, let's see what we have. If you write it out, 1 for I, so it's 1 over 1 times 3, that's the first term. When I equal to 2, have 2 times 2 is 4, 4 minus 1 is 3, 3, 5. 5, 7, and 2n minus 1, 2n plus 1. So this is our nth partial sum, the sum of the first n terms in this series. Well, we very much want to check the limit when n goes to infinity of this sequence, this expression. It's hard because the way it is, if you increase the n, you just increase the number of terms. There are more and more terms. It's impossible to check the limit. Now we'll find a way to simplify this sum. It can be simplified or retracted. That's why it's so called the telescoping, retractable telescoping series. How will we do it? Well, let's do some algebra. The general term. Try to split the fraction, or what we call the partial fraction approach. We hope to find a and b, so this can be split into 2. Applying the partial fraction technique, we can determine a and b, just like before in integration when we were talking about integral of rational functions. Here I can figure out hopefully a and b by observation. Suppose I got 1 just to test it out on top. Actually, since there's no I here, I expect 1 to be 1 positive, 1 negative. Let's just try it out. So if it was 1 1 on top, minus sign there, when we add them up, I would have a 2i plus 1 here. I would have a 2i minus 1, and then we put them together. 2i cancel out. 1 minus 1 would be 2. And then I would multiply this by 1/2. But what I'm saying is, well, it would work out this way. If you check it out, and to simplify, this becomes exactly the left side we started at. So using our partial fraction terminology, you start with the a over minus plus b over. Your a will be 1/2 here, your b will be negative 1/2. Either way, just let me just write out so see better. It be 1/2 here for your a. Do the standard partial fraction work like before. But since this is kind of simple, special, I can get away with just observation. Well, this partial fraction or decomposition result shows that each term can be split into two, like 1 over 1 times 3 is the same as 1/2 1 over 1 minus 1/3. The second guy, 1 over 2 times 1 over 3 minus 1/5. 1 over 2, 1/5 minus 1/7. The last one, 1/2 1 over 2n minus 1 minus 1 over 2n plus 1. Now, everything inside each group is multiplied by 1/2. Notice negative 1/3 and the 1/3. Of course, each multiplied by 1/2 outside. One is negative, one is positive. So those two terms actually cancel each other if you multiply out. The 1/5 negative with the 1/5 positive here, again, each multiplied by the 1/2 in the front will cancel each other. So we conclude that for two consecutive groups, the second term cancels out the first term in the next group. So those two cancel each other, those two cancel each other, those two cancel each other. And you can imagine this guy will get canceled out by the second term in the group right before this. What it means is, in the end, there's 1/2 times 1 remain, and there's 1/2 times this guy that stays. Well, now you see, we started with sum of n terms expanded. Now it's retracted to just two terms, and it's easy to see when n goes to infinity, this goes to 1/2 because it can be 0, meaning the sum equals limit s sub n goes to infinity. We just figure out the limit here. Limit is 1/2. So the original series converges because, well, it equals the limit of the sequence, which is 1/2, finite number. Converges. Now from this example, we use the definition here to determine convergence, divergence. We actually get a better result. We actually find the exact value of the sum. We're able to do this in this example mainly because the S of n can be simplified to that. If the S of n cannot be simplified, well, it will be as difficult to find the limit as how we would try to find the sum in the original series, sum of infinitely many terms. With this definition, we can work on what's called geometric series. Geometric series looks like sum of nth power of the same number multiplied by some constant a. Well, a couple of things here. We first of all need to learn to identify geometric series. And then we'll talk about with the geometric series how we end up with the result using the definition. Basically, given a geometric series, we can construct the nth partial sum, and the nth partial sum can be simplified. Therefore, we can check the limit of the nth partial sum. That's how we would come up with our result here, called geometric series test. So this test is pretty useful if we have geometric series. Just check the R. If the absolute value R is less than 1, the series converges. It actually converges to that, meaning the value of this sum is a over 1 minus r. If the absolute value of r is greater or equal to 1, the infinite series diverges. So we can check every geometric series. As long as it's a geometric series, we know one way or the other. So that's nice about it. So now first, let's become familiar with geometric series. Let's learn to identify geometric series. Two parts geometric series. The main part is nth power, and there's some coefficient. Sometimes you don't see. It's fine. If you don't see number there, that just means it's 1. So this is not important. But what's important is also the R, we call the base, and the A, if there's A, if there's an A there, must be all constants, like sigma 4 times 2 to the nth power. That's geometric series. R is 2 constant, A is 4 constant. Now we don't care where n started out. Just to check whether it's geometric series, doesn't matter n start from what. It's always geometric series. We only care about the starting number, whether specifically is 0 or not, when we know it would converge, and we try to find the exact value, because where the star, of course, will determine what value. Start from 2 or start from 0. If you start from 0, you have 2 more terms, of course. The values are different. But before we get to that, we need to make sure we have a geometric series. The n can start from anywhere. It's still geometric series as long as you have n to the power of r, which is constant, and on A, that's constant in the front. Let's see another one. Sigma n times 1/3 to the nth power. We say the nth power, so r equal to 1/3 constant. Now this time the n, which is supposed to be our index starting from whatever, is not constant, so this is not geometric series. This one is. Let's see another one. Say we have a 3 times 1/n to the nth power. This is not geometric series because the base is 1/n. That's not a constant, so this is not geometric series. Let's see more. Say 4 times 3 to negative nth power. Well, it doesn't look like a geometric series because geometric series we have to have nth power of something. This is negative n, it's not n, but we can rewrite algebraically this as 3 to negative 1 to the nth power. Right? Now I have an a, I have an r, both are constant. So this is a geometric series. Let's see another one. 4 times, say, nth root of 3. Well, obviously it doesn't look like a geometric series. Can we rewrite like we did up here? Let's try. Nth root, you write it as 3 raised to 1/n. Well, this guy, it's impossible to rewrite as nth power of anything algebraically. So this is not geometric series. Alright, so hopefully with this few examples here, it's clear when we have a geometric series. Now let's talk about the result here. Basically, we'll see how we try to use this nth partition theory or definition approach to draw the conclusion here we call geometric series test. Well, it basically works out like this. Say we have a geometric series. N start from 0. Now nth partition, well, let's use I, okay? Use I as the index. The S of n for this geometric series would be, well, 0 to n minus 1. That would give us n terms. Then we write it out. See what we can do, how we can simplify to 1 or 2 terms instead of n terms. I equal to 0, it's a times 1. A equal to 1, a times r squared. The last term, a times r to n minus 1 power. In this one, algebraically, it's same as a product of a. Well, with n terms here, it's impossible to find the limit. Fortunately, in algebra, we can show the sum of those powers equals that. Now, it's easy to see when absolute R is less than 1, this thing will approach 0. This power, nth power, will approach 0. So if we use a definition that we introduced here, then we conclude when absolute R is less than 1, this limit is, or this part becomes 0. So it's just 1 on the top. It becomes 1 over 1 minus R. Also, it's easy to see if absolute R is greater than or equal to 1, either this will approach infinity or there's no limit. So we see undefined, the limit undefined. Therefore, the series would diverge. And this is the conclusion we have in the test. Absolute value of R less than 1, the series converges to this value. Absolute value of R greater than or equal to 1, the series diverges because of this guy here. Less than 1, we can do the limit. This part becomes 0. Greater than or equal to 1, well, either there's no limit or this is infinity. Either way, the series diverges, undefined or infinity. This is how we use the definition to sort of prove, derive the geometric series test. And look at the test here. It's very convenient, of course, assuming you have geometric series. Also, this result here, for this to equal to a over 1 minus r, the n has to start from 0 because this is the exact value. N start from different number, the value will be different, will still converge as long as absolute r is less than 1. Now, if it's absolute r is greater than 1, it diverges. Is nothing we need to worry about. Okay, let's see some examples. Well, see, first of all, what do we have here? We have nth power of e over 10. The e is the natural number, is it? It's constant. So e over 10 is a constant. So r is a constant. Fine. Now what's a? We don't say a. Well, it just means a is 1. That's constant too. So that's a geometric series. Once we realize we have a geometric series, we check r. It's positive. We don't have to take absolute value. It's less than 1. Obviously, e is like 2 point something. Then 2 point something divided by 10 is less than 1. So in this geometric series, r is less than 1. We know it's going to converge. We converge now. Let's see what the text says. Absolute less than 1, it's going to converge. Well, before we try to apply formula, we need to make sure the index will start from 0. If the index is not starting from 0, it's not going to equal to a over 1 minus r. Index in this series start from 2. So we have to rewrite the series as a new geometric series in which a new index will start from 0. So we can apply formula. How do we make a change of index? Let's do this. In the original series, n start from 2. So we write that n equal to 2. Move 2 over. Then we see n minus 2 would equal to 0. If we regard n minus 2 as a new index, it would start from 0. That's how we come up with our new index. It's just to rewrite the same exact series. Now I'm going to replace the n according to this by m plus 2. M equal to n minus 2, so m plus 2 equal to n. This is start to look at geometric series. Let's keep the m as the main exponential term. The second power of e over 10 put in the front that serve as a. So the new series, of course, is still geometric series. Now it's a standard form, like a mth power m index. So this is the a, this is the r, compared to the standard geometric series. When the index starts from 0, that's n, like m there. The sum is a over 1 minus r. So this will equal to a. Now this is a new a, e over 10 square 1 minus r. R is the same. And you don't have the same reply. So it converges to whatever this is. Geometric series. Identify r, see if the absolute value is less than 1 or not. Let's check this series. Well, we kind of see power. It's not nth part of say square 2, so it doesn't look like a geometric series. Algebraically, so anywhere start from 1. Algebraically, it's rewrite. For example, we split the power here and power here. It become square 2 to the first power and the square 2 negative nth power. This guy is fine. It's just like a constant. What we have to do more is to try to see if this can turn to nth power of something. Well, it turns out algebraically it's the same as that. Or we can get rid of the negative power, just have this. Of course, more stuff in 1. So by rewriting, we see indeed this is a geometric series. Now here it's clear r is 1 over square 2. It's less than 1. A is this guy in front. It's a convergent geometric series. Square 2 is 1.414, something like that. So it's a less than 1. It's a less than 1, and we hope to apply the result to get the value of the sum. But here n has to start from 0. Again, here we need to make some sort of change of index, just like this problem. So again, in the original series, n start from 1, move with 1 over, n minus 1 or start from 0. Of course, this is m. So m would start from 0. Power becomes, let's see, m plus 1. You move with 1 over. It says n equal to m plus 1. So m plus 1. And similarly, split. So we have mth power by itself. Split the power. First power here, mth power back here. Well, those two cancel each other. It's 1. So this equals a. This is 1 now. A over 1 minus r. Once the index, new index, start from 0, we can apply the formula a over 1 minus r. I can simplify it. Simplification is not important. This example shows basically when you're given a series that doesn't appear to be a geometric series, you may be able to rewrite sometimes and show it's actually a geometric series. Next series. Well, this is clearly geometric series. R equal to 100 over 99. A, there's no A, there's no number. 1. It's like a 1. And the power, n start from 0, everything. Okay. What is it? Series though, R is more than 1. R is more than 1, series diverges. End of story. Kinda nice. One more. In this infinite series, we see actually n power everywhere, but this is not appearing as a geometric series. Geometric series is a number times n power. We have this n power all scattered out everywhere. Well, what we do is to do term-wise division first. So have 2 to the n, 3 to the n. Because our n powers are everywhere, we suspect we may still have a geometric series involved. And this one again, algebra becomes 2 over 3 nth power, 5 over 3 nth power. Of course, n starts with 0. And we split. We can only have one n power in a series for it to be geometric series. Once we split, we actually find out yes, that's a geometric series, that's a geometric series. N start from 0. Then we check each other one. And here R is 2 over 3. Actually it converges and we would find the value, everything. But this one also geometric series, that's more than 1. This one diverges. Now since this diverges, we don't really care what this converges to. The whole thing diverges. The only purpose of this example is to show sometimes again you can rewrite doing algebraic simplification, rewriting to turn a series that didn't start out to look like a geometric series into geometric series. So you can check that. So in this video we discussed some infinite series, convergence or divergence of infinite series. In summary, in this section, if you recognize series as a geometric series, check R more than 1 diverges, absolute value. Absolute value of R less than 1 converges. You have a geometric series test to apply. Now, if the series is not a geometric series, or because say there's just no n-power at all. So obviously no n-power, there's no way it can be geometric series. Like this, there's no n-power. Or some other cases you rewrite, it's impossible to turn it to a geometric series. If it's not a geometric series, what we can do in this section is to check the limit and hope the limit is not 0. If the limit is not 0, using this test we can say it's going to diverge. Other series that we can do is to use the n-partial sum approach. This is actually the definition of the sum of a series involving the n-partial sum. In order to apply this formula or this definition, we got to be able to simplify the n-partial sum like this telescoping series. N-partial sum start with n terms as expected, but we were lucky to be able to simplify it down to just 1 or 2 terms, finite number of terms, so we can do the limit. Also, it's because of this definition we also proved our geometric series test, and what we use to check geometric series. The n-partial sum can be simplified, its limit can be evaluated. Alright.